I don't know if any of this is still going to happen or not. My guess is not. I do know they are now asking for midterm progress reports, so I have to turn in something probably whenever I can, as soon as I can. This one I kind of doubt if it's going to happen. It's a taxpayer problem-solving day that was to be at Millsap Building on March 31st. I don't think so, okay? So if you told anyone, tell them check before they come, because it probably won't be happening. All right. Let's get going from current slide. And before we do that, I don't know how we're going to proceed from here, okay? Here's my best shot now. My wife has used in her work a package called Zoom, and she's not super great at it, I don't think, but she's way better than I am. And she's said that will work for what you're doing. Now, the free version of Zoom, I think she said only has 40-minute increments. Okay, have you done that?
We used it for my computer science class when our teacher would be there.
Okay. And could he do back-to-back, or she do back-to-back 40-minute segments?
Yes. If you use, there's a code that you get, and you can just re-enter the code that you used to get back.
Okay. All right. So that, I think, is what we're going to try to do. I've never done it. Okay, so it may have a learning curve, but I think my wife's going to be home from her job too, and she said, I don't know how this is going to work, because she likes to have things quiet, and I'll be teaching classes. But we have a fairly good-sized house, so I'll get as far away. I said, I'll go outside if I need to, if our wireless signal goes out there. I think it does. But if that gets spotty, we'll work it out. Okay, so what I'll do, here's my plan anyway for right now until we see if it won't work. At 10 o'clock on Monday, Wednesday mornings, I will try to be there on Zoom as soon as I can get there. I think you can receive this through a laptop or phone, right? If you got a smartphone.
You got to send us the code.
Yes, okay. Now, how did they send that? Through email or?
The way that my teacher did it, she set it up on Blackboard.
Right.
She just put the code on there.
Oh, okay, so it's not just a one, okay, right. I was thinking every time you logged on, you got a code and then you had to send it. Okay.
No, if you set it up, then you'll get the code, and
right.
you can put that on Blackboard, and then that'll be the code that everyone can use for that meeting.
Okay, for that meeting. And then when that 40 minutes is over, you can just re-enter that code and do another 40.
Mm-hmm. As long as you keep the room open. When you close the room and open another one, you'll get a different code.
Okay. I'll put it up again. I'm not here to do that. Right.
She did it with those. She can show you how to do.
Who is this now?
Financial aid works.
Oh, yeah.
So she knows how to do all work is on that. She did it with us.
Okay. So y'all do Zoom meetings?
Like anytime for us, like,
Right. Okay. All right. I'll maybe try to catch her today before I leave. Okay. So get back to people at home can hear. So going to try to do these classes by Zoom. Is it okay to keep doing Monday, Wednesday, 10 o'clock? Okay. And
if I have to work, I can still just checking.
right. Okay. So I'll need to put my code out there on Blackboard. So you'll need to check your Blackboard. And when I get the code, does my time start right then, or do you know?
If you're using the paid one, then you probably won't have a timer.
Right, I know that, but I don't know if we've got access to that. I don't know how much the paid one is. I may go on and buy it, but right now we'll be starting with the free because I don't know how even to go about paying for it, but it's probably not that hard. They'll probably take your money pretty easily. Now, okay, is bandwidth the problem, or do you know it?
I'm not sure. When we
Okay.
did it, all of us were in the computer classroom, and our teacher was the one not there. So we just used the computers in the classroom.
Right. So you probably had plenty of bandwidth. I'm thinking I'm not on a DSL. It's not that bad, but I'm on a CenturyTel or one of those systems. So hopefully I won't have an issue with it. Did your instructor, is it sort of like this whiteboard?
Yeah.
Right.
She was able to put what her camera saw and
Right.
the screen that she
Right. And sound simultaneously. Did you find your sound on your computer was adequate, or did you just use the phone and sound, or?
The sound is good. The way we had it set up was only one of us in the classroom had sound on
Oh,
because
yeah, you're all over there. Right.
But we won't have to worry about that.
Right, you won't have to worry about that.
But yeah, the sound will be good.
Okay, all right. Because Karen said sometimes when she's done them, it's better to have the sound on her phone and the video on their computer screen, but y'all didn't find that necessary. Okay, well, if that happens, you can do that. If you got a laptop and a phone, you can, I'm sure there's some way to log into both. Because I think Karen was doing it with people in India and all over the place, and it could be that the signal would be more messed up from that. How far away was your instructor when she was doing it?
I'm not sure.
You're not sure, just, okay. All right, so that's what we're going to try to do next on Wednesday morning. And I'll try to have it all set up ahead of time. That might mean that our 40 minutes is short, that first 40 minutes, then we'll try to do the second 40 minutes. So I'll need to have on Blackboard an announcement there with the code. But the code, as far as you know, the 40 minutes doesn't start until I log in. I mean,
Classroom.
Yeah, I think as soon as you open it, open the room, it'll start.
okay. And that's when I put the thing out there. So
But what you have to do is you have to set it up like 5 minutes ahead.
yeah, that's what I'm thinking. So 5 minutes will be spent. Yeah.
Log in the Blackboard and
Yeah.
get the code.
Yeah. And since this class is a hour and 40-minute class, it's going to be 3 40-minute segments. We won't use all of the third one, but it's going to be more than 2. So we'll probably have 3, and as far as you know, that'll work too.
They're going to cut you off at 40 minutes.
That's what I think. Yeah, unless I get the paid version. I don't know if I'll get that done in time, but if so,
They'll
I'll
cut
do
you
it.
off at 40 minutes. But if you keep the classroom open, we can log back in.
Yeah.
Okay.
So, what happens when you get, what happens after 40 minutes is it just closes the window.
Right.
So, you just have to go and open it again.
Right.
And I think, well, I don't know which one our teacher used, but all of us used the free one. So we got to use the same code. So I think our teacher used the paid version.
Oh, okay.
So
Do you know if she paid for it or the school had it for her?
I have no idea.
I'll have to find that out. So Miss Lewis knows some of this, right? You said Courtney Lewis? Okay. But she probably, I'm guessing y'all didn't do for more than 40 minutes at a time, did you? Or you did?
We did 40 minutes and it went off.
And it went off.
We got she had told us, I think she gave us a new code.
Yeah, so you got to get, that's what I'm thinking, you got to get a new code.
Yeah.
So once it closes out, it's going to close out.
Okay.
you
So
know-
that means your instructor had the paid, but y'all had the thing so you could use the same code. But if I have the,
Yeah, you got, it's
I'll
gonna
have
close.
to-
Once it closes, then you have to initiate again. So
right, and I'll get a new code.
then you get a new
And,
code, send it to us, and then we'll log on again.
Yeah, but then I have to send it to Blackboard so y'all can know the new code.
If it'll be easier to put it on an email, you can do that too.
Okay. Yeah, because you don't receive this through Blackboard, do you?
No.
No. Okay, so yeah, which is easier for y'all, email or Blackboard?
I don't think it matters.
Okay. All right. Well, actually, to get all of you at one time, I have to email through Blackboard. So I'll just do it as an announcement. It'll send the email as well. So now, when you log on, she was able to see that. Is that right?
Yes.
So
You gotta type her name in.
right.
You'll be able to see how many people are.
Right. So that's how I'll keep my roll, is by who signs in that day. Okay.
And then if everybody just disappears all at once, then time's up.
Time's up. Okay. Well, yeah, their time's up, even if I get the paid version.
Yeah.
Okay. Okay. All right. I'll check with Ms. Glass and see if the school has a contract with Zoom. Because I've heard from another instructor, I had planned to do Zoom, and if so, I was going to find out about it over the weekend. But the dean called last night and told me not to come to campus. So I got to go to campus and get my books and stuff. Oh, okay. I told her I was going to use Zoom. She said, "Oh, what do they call it on Blackboard? There's a package on Blackboard." She said, "Oh, it's better." So I thought, well, then I won't mess with Zoom. I'll use the one on Blackboard. I talked with an instructor this morning. She said, "No, it's not." Okay, because she had used it. And the dean had said, "I just heard about Zoom, but I think Blackboard's better." She said, the one who had used both said, "No, it's not." I was surprised because nothing so far in this new package of Blackboard is very much better than anything that I've ever seen. So,
It's just complicated to use.
yeah. So I'm going to, and it crashes and does things. So I think Zoom is better. All right. I will pursue that then, and hopefully before Wednesday morning at 10, you will have gotten an email message from me and an announcement on Blackboard and everything else with as much instruction as I can do.
So
Okay.
are we not coming back this semester at all?
April.
No, they said April 8th or 6th or something. Huh?
April
6th. Okay. Now, let's talk about that. Y'all know my health condition, right? Okay. My wife is an epidemiologist. She's infectious disease epidemiologist. She studies these diseases. She's had projects with the flu and things like this. She worked at UAB. She has been tracking this disease, and I don't think she's done it. I think something else is done, but she's been tracking. And it shows us and Italy, we're on the same trajectory. And Italy got started much before us, but when you account for that, we're on the same trajectory. Now, I think we have done some things better than Italy did. We stopped sporting events, we closed schools, we did that earlier than Italy did. So we might get under theirs, but the thing is, I am pretty certain that I will not be advised to come back to campus, even if y'all come back on April 6th or whatever day it is. So there's a real good chance we'll continue online. Hopefully by that point, I will have most of the bugs worked out and we can do it fairly smoothly. Okay. So, and frankly, I have doubts about the summer. Okay. I think I'll still be doing online in the summer unless by some miraculous thing this thing is all over, or I've caught the disease and come through it and then I'm immune to it. So I hope that doesn't happen either, but there's actually, my wife, the epidemiologist, we were talking about it this morning. I said, but okay, hopefully sometime in the summer we'll have antivirals that are effective against it. They're still developing those, okay, because it's a brand new disease. But nobody has immunity for it, okay? And the vaccine is at least a year out, at the earliest a year out. So no one's going to have a vaccine for it before then. No matter what the politicians say, they're trying to get reelected. That There will be no vaccine before a year is out. It just, you can't do it. They cannot do it that fast, okay? The antivirals they can do, and they're working on those, and they're hoping. In fact, UAB is working on some, but there's some other people I think ought to jump on them, so, and maybe have some things fairly close to in place by summer. So there's a good chance I won't be back in the summer on campus. I may be doing everything from home. And the fact that the dean called me last night and said, don't come to campus. I said, well, do I need to take sick leave? She said, no, just teach your class from home. So I think I will be allowed to do this. I'm not sure about other instructors, but my condition is sort of exceptional, perhaps. Condition, that's all, just the condition. So, and actually, this is another jump here. Sometimes the flu, of course, goes down in the summer. Now, this isn't the flu, so we don't know what it's going to do. It's been in Australia, which is their summer now, you know, so there's no indication it's going to go. But the Spanish flu back in, this is before my time, so don't imagine I was there to do it, but in 1918, it died down in the summer. They thought they were over. It came back with a vengeance in the fall and just wiped out huge populations. We're a bit more advanced, a little bit more advanced than we were then, so hopefully there will be some thing. But there still will be no vaccine. So when my wife and I were talking about it this morning, I said, well, basically, just about everybody's going to have to get it at some point. The question is whether you spike like this when your healthcare system can't handle that many people, or you prolong the disease and make it flatten out, and then you can have these people in the hospital and then those people in the hospital. Right now, the hospital beds in Italy and other places completely exceeded capacity. And healthcare workers were getting sick and things like this. We've already had 2 MDs, 2 medical doctors, die from this in the U.S. You know, one was in his 40s, one was in his 70s. The one in the 40s, no indication that he had any other, So it can hit anybody. So I said, so basically, we're all going to get it. And she said, well, it's usually a 40 to 70%, 40 to 70% of the people have an immunity to it, then usually the disease will die out somewhat and won't come back with those kind of numbers again. And then maybe by then you can have a vaccine. So that's what I'm saying. I don't think I'll be here in the summer. I may be here on the 6th or 8th or whenever.
So 40 to 70% has to get it.
Yeah, if there's a novel virus like this before, you have what they call community immunity. It sounds nice, doesn't it? But yeah, if that many are immune, have already built up antibodies and stuff, they're not going to pass it to anybody else. So if the disease doesn't have enough vectors, and if everybody still is using social distancing and that kind of stuff, and by the way, y'all are sitting too close together. You can, again, prolong the trajectory until maybe we get a antibody or a vaccine, but that's going to be a year. So if you can put off having it and not get it in that time. So we'll see. But the antivirals may be online by summer. That's the most optimistic prediction right now. So anyway, I intend to be teaching in the summer. I'm I'm on the schedule to teach this summer, but it'll be online. We'll see. No one's thinking past April 8th, okay, or 6th, or whatever the date is, and we don't know beans about that. Okay, but we'll see what's happening. Okay. Now, let's get down to calculus. Okay, is there any other question on that before we get going here? All right, last time, if there are no questions, we had done example 1, and the book goes straight to what's next. So I thought there was a reason I was on example 1. All right. Here is where we're going to do example 2. It's not on the slide set, but we can do it here. And by the way, not on the slide set, but it is at larsoncalculus.com. You can see an interactive version for this type of an example. Okay, this one says use Newton's method to approximate the zeros of f of x is equal to e to the x plus x. Okay? Now, anyone want to try finding zeros some other way for this one? I don't know how. Okay, so Newton's method is just about it. The one we did before, yeah, you could find the zero. You knew what it was. Here, not a clue. Okay? It says continue the iterations until 2 successive approximations differ by less than 0.0001. That is very, very precise. 10 to the minus 4. That's pretty precise. Okay? Now, good thing to do with Newton's method is to get an idea of where the zeros are. Okay? So if you were going to set this equal to 0, now one thing you could do is plug it into your graphing calculator, if you have a graphing calculator, and see what it approximates that to be. Short of that, see, e to the minus is always going to be positive. But once x is minus, that's going to be bringing it down. So let's just pick a value. I know the e to the 0 is going to be 1. And this to the 0 is going to be 1. Okay, and from there it's going to go upward pretty quickly. So there's not going to be any zeros to the right of 0. There will be at least 1 to the left of 0. So let's try another number, like x equals minus 1. Now, if you got a calculator, just plug it in and see. What's e to the minus 1? Anyone bring a calculator today? If you got a phone, that may work. E to the minus 1 minus 1. That will definitely be negative. Right? And in the book it shows it, so if you don't want to look that up, you can. Yeah. Because e to the minus 1 is something on the order of 1/3. Subtract 1 from it, you got minus 2/3, or something of that order. Wait. What's that? E to the minus? E to the minus 1 minus 1, or e to the minus 1? No, it's got to be negative. Okay. Be sure when you do on your calculator let me show you. E to the minus 1, be sure that's in parentheses before you do the next minus 1. Because I think what you just told me was e to the minus 2. It did minus 1 and said it's minus 2. Be sure you do it like that. Comes out a negative number, right? Anybody? Well, it does. Take my word for it. Because e to the minus 1 is approximately, this isn't exact, but about 1/3. Because it's 1 over 2.7, blah, blah, blah. And then when you subtract 1 from it, that's got to be negative. It's approximately negative 2/3. Not exact, but somewhere like that. Something in that range. Right? It's near negative 0.6 is what the book says. Okay? So, what do we want to choose as our first x? Because it's so easy, 0. Okay, you could choose negative 1. It's actually closer to the 0, but I would choose 0. Okay? Well, let's see. I can't tell what the book did, but let's try it. All right, how do we do Newton's method, though? Let's go back a slide or two. Here it is. X to the n plus 1 is x to the n minus f of xn divided by f prime of xn. Okay? So we already know what f of x is. What's f prime of x? Anybody? That's the calculus part. That should be like that, right? What's that? E to the x plus 1. Yeah. There's your F prime of x. Okay? So remember, you do the previous value minus function over its derivative. Okay? So this will be, all right. We said that f of 0 is equal to 1, right? We know that one. That's our last value, our first value. So we'll call this x to the 0, okay? So x to the 1 will then be x to the 0, which is 1, minus f of 0, which is 1 over f prime of 0. Well, f prime of 0 would be 1 plus 1 is 2. So this is 0.5. And that is closer to the solution than we were before. 1 was sort of far off, 0.5 is not bad. Right? Okay. So x sub 2 would then be 0.5 minus, now here you're going to have to use your calculator, so make sure you use them right. Okay? I'm going to write it in. E to the 0.5 plus 0.5 divided by e to the 0.5 plus 1. It's a little awkward, but it's not too bad. Anybody do it? Second? Okay. It's 0.5 minus. Open you up to parentheses there. Okay? And then do e to the 0.5 plus 0.5. Close that parentheses, divided by, open parentheses, e to the 0.5 plus 1. Close that parentheses, get your equal sign. So the best way to do this on a calculator is put parentheses here and here, and that should give you the right answer. Wait, there's something wrong with this picture. That should be a negative. Let me go back and rethink, because we went the wrong way here. F of 0 is indeed 1. And so your first one would be 1 minus 1 over f prime at 0 would be 2. That's heading the wrong direction, folks. That should be a negative. Where have I blown it here? Oh, wait. No, I'm sorry. Our first guess, x of, okay, I've written this wrong, okay. Our first guess was, okay, this is f of x0. That's where I wrote it wrong. Your x equals 0. So this was a 0. So this is a minus 1/2. Now we're okay. Okay. So okay, not quite. All right. Whoa, I was way off there. Whoa, my pen didn't come back. Okay. All right, let's try that again. Our x sub 0 was equal to 0. Our f of x sub 0 was what was 1, okay? So then our f prime, well, we've already done that one. Your x of 1 would then be your x sub 0, not f of x 0, x of 0, which is 0, minus f of x 0, which was e to the, okay, I'm going to take out these things because I'm afraid that's confusing. Okay. Okay. F of x, when x equals 0, f of 0 will be 1. Okay. And this is, okay. Whoops. I'm doing a lot of backtracking here to try to straighten this mess out. Okay. Your f of 0 here is going to be 1. F prime of 0 is going to be 2. Okay? So that's what we're plugging in here. X sub 1 is 0, that's x sub 0, minus this, which gives us minus 0.5. Okay? Now, your next one, x sub 2 is negative 0.5 minus, open your parentheses, and then we're plugging in the negative 0.5, this thing here, into these expressions here. And that would be e to the minus 0.5 minus 0.5 over e to the minus 0.5 plus 1. So that's our next expression. Okay? Be sure you put your parentheses in there. Be sure you use the right number. Okay. Okay? And what do you get? Anybody? Negative 0.5. So you do negative 0.5, then do a minus sign, subtraction sign. Open parentheses, e to the minus 0.5, minus 0.5, close parentheses divided by, open parentheses, e to the minus 0.5 plus 1, close parentheses, see what it equals.
So you put it in the calculator, you're not going to put the whole thing in parentheses?
You could do that.
Okay.
Okay, if you put this whole thing in parentheses, that's okay too, but then when you do this divided by that, you still got to put it in parentheses. So just leave off one set of parentheses. This should work. Now, I don't know if phones will work this way, but most calculators will work that because they do division before they do subtraction. Okay, but if you do it without these parentheses, then it's going to do this, minus this, divided by all that, divided by this, you know, and that's not what you want. No, it'll be divided by this one and then add 1 to it. So you've got to put the parentheses as grouping symbols. So if someone's got this, can you say that again? 66 what? 111? Is that what you said?
It's 3.1.
Say again.
311.
311. Right here. Negative 0.566311. All right, good. All right. We're getting closer because you know the answer is going to be, ooh. In fact, we're awfully close. Okay? So the next one would be x sub 3 would be that value, negative 0.566,311 minus, open parenthesis, e to the minus 0.566,311 minus 0. And this is not part of that, okay? That's that, okay? Minus 0.566,311, okay? Close parentheses divided by open parentheses, e to the minus 0.566,311 plus 1. Okay. Now, hopefully you'll see, if you have a mem key on your calculator, okay, then once you get this, put it in memory. And then you pull that out of memory and do minus e to the recall memory, do a plus recall memory there, because it will pull out the minus sign, close parentheses, divided by open parentheses, e to the recall memory plus 1, close parentheses. That's a lot easier than plugging those numbers every time. But if you don't have the memory key, then punch away. Okay? And I bet you're going to come very close. Because we were already closer than they were after one time, so it's not going to be long. I know punching all those numbers takes a while. But if you look in your book, you'll see we're already really close, and just one more time probably is going to get us about as close as we're going to get. You got anything yet? But Newton's method works incredibly fast, as long as you avoid changes in direction, okay, or horizontal derivative. Because if you have a horizontal derivative, you're dividing by 0. And that will never work, okay? If you have it curving the wrong way, so that first estimate points away from your x-axis, you'll never get there, okay? Because it's going to take you further away, and you just keep getting further and further. We'll see that coming up next. Okay, did you ever get an answer? What's that? The last number, what? Oh, you're putting this one in? Okay. Of course, you would do this actually on a computer rather than a calculator, because you can let it record in memory all your digits there, and you don't ever have to do it. But the answer they gave in the book is negative 0.56714. And we're so close to that. We're within 3 decimal places now. It's not going to take us long to get that 4th decimal place. Okay. I would think this time or the next would do it. We don't need to take. Huh? Okay, is this what you got? 56714. Is that? Huh? 143? Yeah, see, you're within. All we needed was within 4 decimal places. You're within it. So, yeah, that's the answer the book got. You got one more place beyond that. So, yeah. You would do it one more time to see you guys going to get that same answer over and over again. Okay. So, good job on that. All right. Now, Now we're ready for this. When, as in example 1 or 2, we didn't do example 2 on the PowerPoint, the approximations approach a limit, the sequence of the approximations x of 1, x of 2, x of 3, up to x of n is said to converge. Moreover, when the limit is some value c, it can be shown that c must be a 0 of f. Okay, now this picture shows that. What they're showing is what to avoid. Newton's method does not always yield a convergent sequence. One way it can fail to do so is shown here. If that first value you choose gives you a 0 derivative, it fails right there because you can't divide by 0. Ever. Okay? Now, if you had started up here, you're probably going to get there missing that 0 value. If you started down here, you'll certainly get there. Okay? But if you started somewhere that pointed you in this direction, which it doesn't look like any of these will, but if you happen to start there, bad luck, you blew it. Okay? You're not going to be able to get a converging sequence. Okay? Now that's one case when it doesn't. Okay? Because Newton's method involves division by x prime, the first derivative, it's clear that that method will fail when the derivative is 0 for any x of n in the sequence. So if you did happen that happened to you, it fails automatically. Stops right there. When you encounter that problem, you can usually overcome it by choosing a different first value. Okay? Now another way it can fail is shown in the next example. Okay? And they're not going to show it to us, they're going to make us do it. Okay? So here's what we've got. The function f of x is equal to x to the x to the 1/3 power. Now, remember what you need for Newton's method to work? You need to know f prime of x, right? Okay? So what is f prime of x? If that your f of x, one-third x to the negative 2/3. Perfect. Which you could write, you don't need to, but you could write this way, 1/3, and then put this x to the 2/3 in the denominator, and that would be the cube root of x squared. That's what x to the minus 2/3 is. Okay. Now, what we're looking for are the zeros of this function. Can anyone guess what the 0 of that function is? Where is this function equal to 0? When x is equal to 0. Well, what happens here to your first derivative when x is equal to 0? Undefined. It doesn't have a first derivative, is not differentiable at x equals 0. And that's what you're trying to go toward. So what happens then, whatever you do, the closer you get to 0, the more it blows up. So it takes you further and further from 0 to keep from blowing up. So you're not going to get there. Okay? So if either your first derivative ever comes up being 0, you have to stop. It's not going to work. You can try a closer value. But if your function itself is not differentiable at that 0, which in this case it's not, then it's not ever going to work there either. And choosing some other value isn't going to help you any. Okay? And without going through some really ugly, gory detail here, I'll just let them explain what happens. Because f prime is that, the iterative formula is x to the n plus 1 is x to the n minus f of x of n over f prime of x to the n. Okay? And we know this 0 is going to be at x equals 0. Well, the closer you get to x equals 0, this thing explodes. I mean, really bad. Okay? So what is happening then? You have x sub n to the 1/3, that's your f of x, over 1/3, just like you said, x sub n to the negative 2/3, which if you rewrote that, that would be x sub n, okay? And you see your denominator is this thing right here. Well, when you flip that over, since you're doing the denominator, dividing by this with multiplying by that, you get a 3 up top, and you get this up top, multiply it by that, and you get x minus 3x of n.
Hey, I just came to pick up my test. My parents came to my house today.
Okay?
Thank you.
And we're working on the last example that goes with the last question.
Thank you.
Okay. Oh, and by the way, we're going to be online from now on.
Yeah.
Yeah, okay. You do that. Okay. Okay.
Yeah, I didn't come to class because my first teacher did it online.
Uh-huh.
And then I thought we didn't have class today, so I just decided to help my parents out, and now they really need my house. So.
Right. Okay. You got to get yours too. Boy, he started a trend, didn't he? Okay. Okay. Let me.
I thought you had already given her out. You was gonna give it the end of class.
Oh, I see. She's just got to get an edge on you guys, you know? Yeah, I see. Uh-huh. Okay. All right. So you see, this actually becomes this over that, which when you divide by that, it flips it up and multiplies. So that's where you get the 3 in the numerator, and then this x of n to the 1/3 times x of n to the 2/3. That's just x to the n. So that gives you xn minus 3xn. So that's going to give you x sub n, whatever you chose that first value to be, times negative 2. Okay? So what happens? Say you chose 0.1 as your x of n. Your next x of n would be negative 0.02. The next one would be positive 0.04. Next would be negative 0.08. Next one, positive 0.16. You know, they're getting further and further from the 0, not closer and closer. And the reason is the derivative is not defined at 0, so it's taking you further and further away. Okay? Minus 2x of n. That's what I have. I wrote it differently. So, if you chose, and I can't believe this, they chose 0.1 also. Okay? And your x of 2 would then be, they went through all the calculations to give you that, if you did all that, but goodness, save yourself some effort, just do what they did there. Negative 0.2, positive 0.4, negative 0.8, positive 1.6, negative 3.2, positive 6.4, further and further and further away either direction. Okay? Not going to help you. Not going to take you anywhere close to your 0. Here is a picture of that. If you chose your 0.1 here, there's the 0, 1. 0.1 would be here. Got here. Your slope takes you down here for your x of 2. That's the negative 1, 0.02. Then this slope takes you back this way, positive 0.4. This one takes you back here, negative 0.8. This one takes you back here, positive 1.6. This one would take you over here, positive 3.2, negative 3.2. Further and further and further away from the real 0. And the reason is your derivative is not defined. So you can't possibly get anywhere close to that value. In fact, it keeps taking you further and further away. Okay. So, 2 situations where Newton's method doesn't work. 1, if it happens to fall on a point, one of your estimation points has a 0 derivative, it'll never work then. okay? You might be able to guess a point other than that and avoid that zero derivative. But if you have one that has an infinite derivative, in other words, the derivative is not defined at that point, even though there is a zero there, it's never going to work. It can't possibly work, okay? It can be shown that a condition sufficient to produce convergence of Newton's method to a zero is that the absolute value of the product of the function, its second derivative, divided by the first derivative squared, if that is less than 1, you will convert it, okay, on an open interval that contains a 0, okay? So what you have to do, you started with the function, take its first derivative, go on and take the second derivative, okay? Multiply the function by the second derivative, divide it by the first derivative squared, see if that's less than 1. If it is, you're okay. Pick a point and go from there. All right. If you're in an interval that contains that 0. Now, what about this one? You need to do Newton's method on that to find the 0 of the function. Second? Now you could, perhaps, and I think the derivatives will work out fine, but take a look at this closely. If you factor in x2 out of, anytime you have an even number of terms, 4, 6, 8, whatever, look at it and see if possibly factoring by grouping will work. And sure enough, if you factor this by grouping, you get x squared times x minus 2, right? Group these two together, you get -1 times x minus 2. Now, you can factor that by grouping. We found by simple algebraic techniques such as that. How about this one, though? This will not work. Newton's method is your only shot to find the 0 here. Yeah, you can find that elsewise there. This one, you can't factor that. I can't factor that. I don't think anyone can. Cannot be found by elementary algebraic methods. So Newton's method, okay? Now, let's see if they tell you. Yeah, this particular function has only one real 0, and using more advanced algebraic techniques, which we don't have here, gives that 0 to be minus the cube root of 3 minus the square root of 23 over 3, one of my favorite numbers, divided by 6, minus the cube root of 3 plus the square root of 23 over 3, divided by 6. Oh yeah, why didn't I think of that one, okay? Because the exact solution is written in terms of the square roots, and cube roots is called a solution by radicals. We're not going there. They can tell us this, but goodness gracious, we don't have the tools in our toolkit to come up with that solution. Newton's method, far easier. In fact, Newton's method, far easier than even writing that stuff down. Okay, it's a pain. Okay. And that is the last slide in the section. Now, they did have a little blurb right after that. The determination of radical solutions by polynomial equation is one of the fundamental problems in algebra. The earliest such result of the quadratic formula, which dates back to at least Babylonian times, the general formula for zeros of the cubic function were developed much later. In the 16th century, an Italian mathematician, Jerome Cardin, published a method for finding radical solutions for cubic and quartic. Then for 300 years, the finding the general quintic formula remained open. Finally, in the 19th century, the problem was answered independently by two very young-looking mathematicians, okay? Niels Heinrich Abel, a Norwegian mathematician, and Évariste Galois, a French mathematician, proved that it is not possible to solve a general fifth or higher order general degree polynomial equation by radicals. Okay? There are some, but not in general. They give the pictures of these two. They were very young, and the pictures here, I don't think the greatest pictures I've ever seen, but they both died at very young ages. Abel died at age 27, and Galois died at age 21. Okay? And they lived similar times. I mean, they were, Abel was 9 years older than Galois, but he died just 3 years earlier than Galois. I don't know how Abel died. Galois, in addition to being quite a brilliant mathematician, I think turned out to be a jerk as well. If my memory's right, and I'm just doing this by memory, he was messing around with someone else's wife, got challenged to a duel and lost. Big time lost. Completely lost, okay? Absolutely unnecessary, and yet there went a very brilliant mind. Never mind, we won't go any further. That finishes 3.8. There's always the concept check. Always take a look at those. You can do any of the, either 3 or 5. They're both at Calc Chat. 3's at Calc View. Any of the odds 7 through 17, they're all at Calc Chat. 9's at Calc View. 19 or 21, they're both at Calc Chat. 23 should be at Calc Chat. 25 should be at Calc Chat and Calc View. 27 and 29 are both at Calc Chat. 31's at Calc Chat. 33 or 35 should both be, you can explore doing those at Calc Chat. 37 and or 39 should be at Calc Chat. There's a couple true false, 41 and 43. They should be at Calc Chat. And 45 should be at Calc Chat. Now, if you need some more practice on doing anything from this chapter, the review exercises are also odd number exercises are at Calc Chat. 1 or 3, 5, 7. Now, none of these are at Calc View. Any of the odds 9 through 19, 21 or 23, 25, 27. Any of the odds 29 to 41. Any of the odds either 43 or 45. Any of the odds 47 to 53, 55. Any of the odds 57 to 81, a whole bunch of those. 83 to 87, 89 or 91, 93, and somewhere there you probably get into some of the stuff we skipped, so don't sweat those. Implicit differentiation, though, we didn't skip that, so 97 to 101, 103 or 105, 107 logarithmic differentiation we did. Then those with inverse functions, you can try them if you'd like. You don't need to, but you can look at those if you'd like. We did do related rates, so you can skip 119. They're fun problems to do, so if you want to do them, you certainly can in 121. And then using Newton's method, you can do any of the odds 123 to 127 and 129. There is a little blurb there on problem solving. If you're interested in that, you certainly can look at that as well. The only reason I sort of mentioned it on page 204, there is a thing called the Padé approximation. I don't even know who Padé was, but he's somebody, it's a potential paper topic. Who in the world he was, how he came up with this approximation, who uses this approximation. There could be several paper topics there. Number 15 may also lead you to investigate, but don't think of it. It says acceleration and jerk. That's not a mathematician. Jerk is the third derivative of a motion problem. First derivative gives you velocity, second derivative acceleration, third derivative gives you the jerk. That's not making any commentary on a person. That's that. Okay, let's move on. How are we doing on time? Oh, I'll see right now, 11:12. Okay, so we've got about 28 minutes. Okay, 28 minutes. The old gray cells are not too swift. Okay, so let's get out of this and move on to chapter 4. Okay, and while this is coming up, I will pass to the rest of you who didn't try to get a jump on everybody else your test for chapter 3. And the one at the bottom is a Newton's method. It just says do 2 iterations, put both answers down there. Okay? The first iteration, then the second. You don't have to carry it to any level of precision like they did in the book. Just do it twice and see what you get. Okay. So chapter 4 is now applying differentiation. Okay? And guarantee you there's a motion problem. There's in fact, most of these look like they could be motion or other rate problems. So 4.1, this is one really classic example of an illustration of application of differentiation, and that's finding the extrema. What in the world is an extrema anyway? That's plural for extreme. I guess extreme must come from Greek or Latin one. I don't remember which. I think it's Greek. And so a plural there is not with an S, but with a changing the last letter from an E to an A. So this is, what is that? It's what are those? Because this is a plural form. So our objective here is to understand the definition of extrema of a function on an interval, understand the definition of a relative extrema of a function on an open interval, and find extrema on a closed interval. So those are the 3 things we'll be looking at in this section. So what are the extrema of a function? In calculus, much effort is devoted to determining the behavior of a function on some interval I. Okay? For instance, does f have some maximum value on that interval I? Does it have a minimum value on that interval I? Where is the function increasing? Where is the function decreasing? Those are all questions that calculus seems to be fascinated with. In this chapter, you'll determine how derivatives can be used to answer all 4 of those questions. Okay? You will also see why these questions are important in some real-life applications. So it's not just a mathematical exercise. So here's your definition of extrema. Let's let f be defined on an interval containing the point c. So here's the interval, and these are all x's here. C is somewhere in that interval. Okay? Now, this f of c is a minimum of that function f. Okay? The interval is along x. It's going from here to here, say. That's along x. We know what the minimum here is, the last one, the maximum here. That's not what we're talking about. We're talking about the minimum of the function on that interval, okay? And the maximum of the function on that. So f of c is a minimum of f on that interval I when f of c is less than or equal to all the other f of x's for all x's on that interval I. And it's a maximum when f of c is greater than or equal to all the other functional values there on that interval I. The minimum and maximum values of the function on an interval are the extreme values or extrema. Okay? Extreme, okay, values, okay. The singular form for extrema is extremum, like mom, mama, okay. So plural is extrema. Of that function on the interval. The minimum and maximum of a function on an interval are also called the absolute minimum and the absolute maximum. Nothing gets below it or above that, okay? Or the other name for it is global minimum or global maximum. Absolute, global, they mean the same, okay, in this context. Extrema can occur at either an interior point or at the endpoints of an interval. And we'll show this in figure 4.1. Extrema can occur, that occur at the endpoints are called endpoint extrema. What a clever name. All right, so here's what we've got. A function need not have a minimum or a maximum on the interval. Okay? For example, in figure 4.1a and b, you see that the function f of x equals x squared plus 1, that's a good old parabola here, but if your interval, it has both a minimum and a maximum on the closed interval from -1 to +2, okay? The minimum value here will, of course, be 0, 1, okay? The vertex of that parabola. The maximum value on the closed interval is going to be here at 2, okay? That's greater than any other point on here. This is less than any other value in this interval, -1 to 2. However, if we have an open interval, -1 to 2, then that doesn't count this value and doesn't count that value. You still have a minimum, but there is no maximum value. Because guess what? If you're not counting the 2, how do you know what's the next one? It's the number closest to 2, but there is no number closest to 2. You can get closer, and no matter how close you get, you can always find another number closer. It doesn't have a maximum, okay? It would have been 2 if you included it, but it's not. Well, the value would have been 5, okay? So get this. The x where the minimum occurs is x equals 0. X where the maximum occurs there is x equals 2. But the minimum value is 1, and the maximum value is 5. That's the function value, okay? Over here, the minimum again is at 0, x equals 0, and the minimum value is again 1, but here we don't have a maximum, okay? Number 1, it would have been at 2, but 2 is not included. There is no number next largest to 2 because you can always get something closer. And then there is not a maximum value because it's not 5, but again, whatever value you choose close to 5, you can always find one closer and closer and closer. So there is no maximum value there. Moreover, in the C one here, you can see that continuity or lack of continuity can affect the existence of this extremum on the interval. What if you had this piecewise defined function that your g of x was this same parabola for all values of x except x equals 0, okay? At x equals 0, you define this to be 2, okay? Well, then, you don't have a minimum because that would have been your minimum there, but you define that value x equals 0 to be up here, so there is no minimum value. There's something closer on this side and that side, but you don't know how far you can get. G, though, is a piecewise defined function. In other words, it's not a continuous function, so the point of discontinuity happens to have been where your minimum would have been, but it's not there anymore. Okay, so this suggests the theorem below. If f is continuous, not discontinuous, continuous on a closed interval, a to b, then f has both a minimum and a maximum on that interval. If it's closed on that. The endpoint is either going to be, and again, it can't be discontinuous, so there is going to be a minimum, either somewhere in the interval or at one of the endpoints, and there's going to be a maximum somewhere in the interval or at one of the endpoints. There has got to be a minimum and a maximum on any continuous function, not discontinuous, on a closed interval, not open. There will always be a minimum and a maximum. All right. Let's move on to relative extrema. And then we're going to introduce the most important concept in this chapter, I think, or at least in the first part, critical numbers. Whether we get there today or not, I don't know. We're awfully close. How are we doing?
11:23.
23. Okay, so we got 17 minutes. Let's see what we can do. In figure 4.2, the graph of f of x is equal to x cubed minus 3x squared has a relative maximum at the point 0, 0. Okay? That's not an absolute maximum, and we'll see that in a minute. And a relative minimum at the point 2, negative 4. Okay? Now, notice they didn't give us an interval here. They just said it has it. Well, this cubic function here, if you keep on going down here, it just keeps on getting more and more and more negative. So there is no absolute minimum, because no matter where you go, you'll find something less. Similarly, over here, it just keeps on climbing and climbing and climbing, never peaking. Okay? So it's not going to have an absolute, excuse me. Hopefully I can get away with just one. Okay. Okay. So what we call these are relative maximum and relative minimum. So that's a new concept. And formally, for a continuous function, you can think of a relative maximum as occurring on a hill of the graph, and a relative minimum is occurring in the valley of that graph. Okay? Now notice we have to keep a fairly small interval around those, because this is a relative maximum, not if you included the interval here, because these numbers way exceed this one. Or if you included the interval here, this wouldn't be minimum, because that one is less than this value. But if you keep your interval small enough, then you can find a relative maximum and a relative minimum. Okay. Such a hill and a valley can occur in two ways. When the hill or valley is smooth and rounded, the graph has a horizontal tangent line at the high point, or the low point, either one. Okay? Let's go back and look here. This is a nice smooth curve here. Here, the first derivative would be positive, 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 positive. But now it starts getting less and less positive, and then it goes to 0 right there. And then it starts going negative. So that is one clue of where your relative maximum is going to be. The first derivative. The first derivative down here is a pretty steep negative. But here it gets a little less negative, less negative, less negative, until your first derivative here is 0. And then it goes to be positive again. That lets you know that's a relative minimum. Your first derivative is your friend. Okay? So when the hill or valley is smooth and rounded, the graph has a horizontal tangent line at either the high point or the low point. Now when the hill or valley is sharp and peaked, the graph represents a function that is not differentiable at that high point or the low point. If it's like this or like this, okay? Your first derivative is not defined here, because it's one thing coming this way, a very negative number, something else very positive coming this way, and there's no in between. So here's a clue where either the first derivative is 0 or the first derivative doesn't exist. Those are your potential places for your extreme values. We jumped ahead a little bit, but it's okay, because here they bring it right up. Definition of relative extreme. If there is an open interval containing C on which f of C is a maximum, then f of C is called a relative maximum of f, if there's some open interval containing that. And you can say that f has a relative maximum at C f of C. C is the x value, f of C is the y value. If there's an open interval containing C, on which f of C is the smallest value in there, then f of C is called the relative minimum of f, and you can say that f has a relative minimum at C f of C. The plural of relative maximum is relative maxima. The MUM is singular, the MA is plural. Okay? I don't know if you're familiar with, he's an alumnus of this school, right? But if there's more than one, they are alumna of the school. And then there's singular, I mean male and female, both of those. It really gets complicated. But that, I believe, is from Greek. I don't think it's Latin, but I believe it's Greek. One of those two anyway. Okay? And the plural of relative minimum is relative minima. Not inima, I'm not going to call it. Okay, the relative maximum and relative minimum are sometimes called the local maximum or local minimum. If you don't want to use relative, remember before, absolute and global meant the same, relative and local mean the same. Okay. If your relatives are local, okay, no problem. So here's example 1. I'm not going to do much of this except show you pictures, okay? Find the value of the derivative of each relative, well, no, you're going to do a little something. Each relative extreme and solve. Now, here is obviously a relative maximum, okay? How are you going to find the value? Okay, find the value of derivative at this relative maximum, at 3, 2. Okay, here's your function, 9 x squared minus 3 over x cubed. So how are we going to find that derivative? What would be your f prime? Okay, 9 times, okay, what are you using here? Yeah, and what rule are you using to take a derivative? Say again? I can't hear. Quotient rule, exactly. And how does that go? Okay, now it goes low d high minus high d low. So if you're going to use the quotient rule, which is it's not the only rule you have here, but it's the one that I think would come first to mind. Low is x cubed times derivative of the numerator. What's the derivative of the numerator? 18x. Perfect. Minus high, which is 9x squared minus 3. D low is 3x squared over x cubed squared. Low. Okay, so that'd be x to the 6th. Okay? Well, let's see what we can do to straighten up this mess. Okay? Perhaps I was real tempted to just want to multiply that through anyway. I think that would have made life a lot easier, but there's some reason they didn't. But let's do it and see what we get. When you multiply these two together, you get 18x to the 4th minus, now let's take these carefully, minus 9 times x squared times 3x squared would be a minus 27. I can't write, I can't talk, I can't do anything. Okay, let's try that again. Minus 9 times x squared times 3 x squared would be minus 27x to the 4th. Okay, And then when you do the next term, it'd be a minus 9 times minus 3 is plus 27 times 3 is 81 plus 81 x squared. All divided by x to the 6th. I hope I'm doing this right because this is a mess. If you add these two together, you get a minus 9x to the 4th plus 81 x squared over x to the 6th. We'll factor out an x squared, and that gives you minus, let's factor out a 9 as well. Let's factor out a minus 9. Okay, let's do that one. And that, I'm sorry. Factor out a minus 9x squared. Factor out as much as you can. Minus 9x squared, and that leaves you x squared minus 9, right? And in the denominator you have x to the 6th. So the x squared will take out 2 of those and leave you x to the 4th. So what we have is minus 9. Let's go on and factor it a little bit further. X plus 3 times x minus 3 over x to the 4th. Okay. Now, let's find what that is when you are at the point 3, 2. So when x is equal to 3, when x is equal to 3, this goes to 0, doesn't it? Right? You factor that one, and you want to know the value of your derivative at this relative maximum. They told you this. We didn't find it. It's going to be at x equal to 3. Okay? And at x equal 3, this is going to be 0. That makes the whole numerator 0. So stop right there. F prime of 3 is equal to 0. Okay? Now, if you do f prime of the absolute value function, well, I know what the slope of this is coming down like this. That's the slope of negative 1. But the slope going up this way is positive 1. So what's the value here? Undefined. The limit as you come from the left is minus 1. The limit as you come from the right is plus 1. Never going to meet. So that is undefined. F prime does not exist. Okay? Now here's your sine function. Okay? F of x equals sine x. Let's see what the derivative is. What is your derivative of sine? F prime of x is equal to, anybody know? Say that again. That's log x. Sine x. What's your derivative of sine? Cosine. Okay. Cosine x. Okay, we know the maximum is here at pi halves 1. So let's plug in when x equals pi halves, what is cosine? Cosine of pi halves. Cosine of pi halves. Okay. Picture your cosine function. It starts here at 1 and it goes down to 0 at pi halves. So that's 0. Okay? Your other value, where you have a relative minimum here, this is at 3 halves pi, where it's at negative 1. Well, what's the cosine of 3 halves pi? 0 again, because here it's 1, 0, minus 1, 0. Sure enough, it's 0 there. So f prime at pi halves and 3 halves pi is 0. Every time you have a first derivative equal to 0, you're going to have, okay, I'm taking that back. In these cases, your maximum and minimum were at x equal, your first derivative was 0. In this case, the first derivative is not defined. Okay. I almost said every time. You can't say every. You never say never, okay? You can't say it every time. All right, so here's what we're going to do. They took the derivative just like we did, and they came out the same thing we did, only they wrote, I put the minus 9 in front, they put the 9 minus x squared. Both things work. And at the point 3, 2, the value of the derivative f prime is 3, with x is equal to 3, when x is equal to 3, 3 squared is 9, 9 minus 9 is 0, that derivative is 0. It doesn't matter what the denominator is, that numerator, if one of the factors is 0, the whole thing is 0. Okay? So that is a x equal, at your maximum value, the derivative is 0. In this one, the derivative does not exist because the limit from the left is minus 1, the limit from the right is positive 1, and never the twain do meet. Okay, in the C part, the derivative of sine is cosine, and at the point pi halves 1, the value is cosine of pi halves is 0, and at the point 3 halves pi negative 1, the value of the derivative is also 0. All right. Flip to page 208. What's that? 2 minutes? Okay. Sort of just to get this in. Well, maybe not. We'll begin next time at the top of page 208. But it'll be noting in example 1, so we'll be referring back to that. Hopefully I'll have everything set up so we can. We almost finished 4.1. I think you can do any of the odds 5 through 9. They should all be at Calc Chat. 5 should be at Calc View. And we'll stop right there and pick up the rest of those next time. All right, any questions? Okay, you do not need to come to campus. Have they come out with anything official yet?
Yeah, they said they said that today was the only day that we would be having classes
On campus. Right.
And then Tuesday there's no classes, but then Wednesday.
Oh, Tuesday is no classes?
No
Tuesday
classes.
is no classes. That way teachers have time to set up, I guess. I don't know. But
Okay. When did that one come out?
It's posted on the, there now.
I got the email late last night.
Okay.
So,
Because the one I heard before that was we were having classes today and tomorrow and then start online on Wednesday. But they've changed it now and say no classes at all tomorrow. Okay. Okay. Now, did they say anything about instructors on that one? Did they say we would be on campus tomorrow?
I don't know. I didn't see anything.
Okay, I think that was probably to us, not to you. I probably will not be on campus tomorrow unless I have to come because I forget something today.
How long you gonna give us?
For what? Oh, the test? The after spring break. Okay. Usually I give you a week, but 1 week from today is spring break. Okay. So I want you to turn it in during spring break. Yeah, no. So when, okay. And what you're going to need to do is, however you can get it back to me. And I would say the best way is scan it and email it to me. It could be that by then I will have figured out a way in Blackboard to get things returned to me that way. But I think the only way to do that is on multiple choice things. I can't think, have you ever taken a test?
I have, but all of them were supposed to be multiple choice.
Were multiple
I
choice.
don't know if it's optional or not.
I don't know how you can do a short answer on those kinds of things, because what you do is you take the test there and I just grade the result. Yeah.
Are you still come on Fridays? Are you still come on Fridays after spring break?
Am I doing what on Friday?
No, I'm talking about Friday. We still running
No.
Friday.
No, I'm not going to be on any campus anymore after today until either April 6th or even if everybody else comes back April 6th, if the pandemic is still increasing in Alabama, I probably won't be back then. I can't say that for sure, but I just know that the dean called me at home last night and said, don't come to campus tomorrow. Everybody else has to, you should. I said, I've got to go and pick up my book. And since I was going to be here anyway, I wanted to get you your test done and get everything else done that I could before I'm confined at home. And I probably will be. Now, I don't know where I'm going to be during spring break. Last week, we were told we could not go out of state because last week, now y'all could, but we could. Because last week there were no cases in Alabama and all the states around us had cases, so we couldn't leave the state unless we self-quarantined for 14 days after we got back. But now that Alabama has plenty of cases, we're no better off, and we wouldn't have been last week anyway. It's just we hadn't. When they were saying that, we had tested no more than around 50 people in the whole state, and they hadn't gotten results back from them yet. So
How many do we have now? How many cases do we have now?
last I heard was in the 30s, I think.
Last night will change by this morning.
Is what?
So whatever they said last night will change by this morning.
Yeah.
This afternoon it'll change again. So
Yeah.
keep up with it.
Yeah, it is completely unknown, but it's all over the place. It really is. Most people, it's not going to be an issue for. But people who are over 60 and people who have suppressed immune systems, it's a problem, okay? And not just people over 60. Like I said, a doctor had died somewhere in the U.S., Colorado maybe, who was in his 40s. And, you figure he would have been fairly healthy. So it can hit anybody, anytime. You're much less likely. Believe it or not, the group of people who are affected the least by it are young kids. This is unlike the flu in this respect. The flu usually was most deadly toward kids and old people. Now it's just the old people. But everybody in there can die, and they can die of the flu too. But this is a different animal, okay? Completely different animal. Some of the models are similar, but it is a completely different strain. And nobody has any immunity to it except those people who have survived the disease and are now healthy again. They are the only people who have an immunity. And what we don't know is if the disease can mutate, because it could be just like the flu changes every year, and you can get the flu multiple times. We don't know whether this is going to be that way or not. But hopefully by the time it does, there will be shots you can take for it that will minimize the effect. Just like flu shot doesn't guarantee you won't get the flu, but it does minimize your severity and minimize your risk of catching it. So it's going to be a mess. And what the worst part of the mess is, our healthcare system is not prepared for it at this rate. If we can smooth it to this way, then we'll be able to handle it. But that doesn't mean people aren't going to still get it. And people over 60 and with immune problems, we're still going to be at risk, even at that kind of a curve. So I don't know. I don't know when I'll be back. I told my wife this morning, I said, this could be my last day teaching at Lawson State. At Lawson State. I'll be teaching still, but I may be teaching at home, because if this comes back with a vengeance in the fall, I may not be here in the fall either. I'll either be retired or I'll be teaching online at home. So, and since the dean said, don't come to campus, I said, I've got to. Oh, yeah, you do have to get your stuff. So, but I won't be back until I get the okay, both from my doctors and the school and my wife, okay, because she's on top of this. Good deal.
See you on Wednesday.
Okay, yeah, you may actually see me, unfortunately. The Screencast-O-Matic, I don't get a picture of me, but on this new thing, you do see me, don't you?
Yeah.
Okay, I'll try to stay out of the camera view as much as possible. Okay, no reason to put you through that too. All right, Take care, folks.